Hi there. There's a couple of things I wanted to just mention about the bonding and shapes worksheet. So things that came to my attention were that we seem to be having trouble between figuring out whether a substance is polar or non-polar, and we're having a bit of trouble between ionic and polar covalent bonding. So let's just recap on a couple of things. I'm going to take two substances. I'm going to take sodium chloride and hydrogen fluoride. So those two substances, I'm going to look at the type of bonding in them. Now the way you find the type of bonding is that you look at the electronegativity differences between the elements. So sodium has an electronegativity value of 0.9 and chlorine has an electronegativity value of 3. So when you subtract those two, you get 2.1. So that's obviously greater than 1.7. So it's probably ionic. Now, I want you to double check if it's ionic or not. Are the two elements, one element should be a metal and the other one should be a non-metal. So sodium is a metal and chlorine is a non-metal. And when that happens, then you definitely have ionic bonding. Okay, no doubt about it. Now HF, let's have a look at HF. Fluorine has an electronegativity value of 4 and hydrogen of course is 2.1. So when I subtract those I get a difference of 1.9. Now the difference of 1.9 is again greater than 1.7. Double check. Is it ionic? You double check. You look at the two elements. If one of them is a metal, then it's definitely ionic. However, they're both non-metals. So both non-metals. And since that is the case, then I'm going to say that this is not ionic. It is strongly polar covalent. Strongly polar covalent. Okay, so you've got to really pay attention to that sort of thing. Maybe I didn't state that clearly in the lesson. The other thing I want to say to you is that an ionic compound like sodium chloride, ionic compounds, they're shapes, right? They're crystals. And every, we'll say, compound that makes up a crystal has a specific shape. You get all different types of shapes of crystals. There's an entire field of chemistry studying crystallography, which is the shapes of different crystals formed by compounds. Sodium chloride, its shape, therefore, it's an ionic lattice. Now, the lattice is this three-dimensional repeating unit. It has a three-dimensional repeating unit, and that determines its shape. So an ionic compound will have an ionic lattice, which determines its shape. So this lattice will determine the shape of the molecule. Now, it won't be any of the shapes of covalent molecules. So it won't be things like pyramidal, tetrahedral, V-shaped. It won't be anything like that. It will be things like cubic-centered lattice or face-centered lattice, this sort of thing, which is beyond our scope. So we don't need to know any of these things. All we need to know is that an ionic compound, its structure or its shape is a strong ionic lattice, and because you have such strong electrostatic forces between the elements, then strong electrostatic forces between the elements in an ionic lattice. This gives you very high boiling points. Okay, right. Now come over here to hydrogen fluoride. Again, it's strongly polar covalent. It's not ionic, strongly polar covalent. So it has because it's strongly polar covalent, it has centers of positive and negative charge separated from each other. So fluorine pulls all the electrons over, and hydrogen, it then ends up slightly positive. So this area here is electron rich and this is electron poor, or electron deficient. So what we have then is we have centres of positive and negative charge separated by each other, and that's known as a dipole. Now, if you have a dipole present, that means the types of intermolecular forces that compound will have will be dipole-dipole forces of attraction. Dipole-dipole. So if you you have a HF here and a HF here, This will be slightly negative end, this will be the slightly positive end. You will have forces of attraction between those two molecules, and this force of attraction is known as a dipole, and it's permanently there. So that's known as a dipole force of attraction. It's there the whole time in a strongly polar covalent molecule.